generalization, also the solution, the nice solution, is why don't we build up a, think about, right, what we did. So we add a cache, right? We build up the memory hierarchy, which not directly access the main memory. Instead, we access the cache first. So why don't we add additional level of caches to further minimize the penalty? So this is the key idea. This is how it looks like, right? With our 2300 microprocessor. Okay, so over here we have, right, this instruction pipeline, right? We have the first level cache, right? See here in two space, right? This is what I mentioned before. We are using the dollar sign, right, to indicate the cache. How about, and this small caches, right, has a size of in the order of kilobytes. Kilo means right, 1024, right? K is 1024. So why don't we insert something in between? So why don't we add a larger cache with a size in the order of megabytes? But this one is lower. This one is not going to be fast enough to be plugged into the processor pipeline. But this one is much faster than the main memory, than DRAM. So this is actually the solution these days. Okay. And we build up a larger SRAM, but there's this compromise, right? So there's a larger SRAM, it's going to be slower, and also we cannot afford to have a high associativity in this kind of cache. We call it L2. L2 means level 2 cache. In the modern processor, in many cases, we have even more levels. We may have 3 levels in some cases, okay, just to further minimize this penalty. So in case you're not convinced, right? First, let me just quickly go through the this dry definitions, right? L1 means level 1, right? This is the small cache, fast, right? Which we can afford to, right, add to the pipeline without hurting the clock frequency. L2 is a larger SRAM. So why is this lower? Any ideas, please? I think some of you are already asking, right? Why is this lower intuitively in terms of the cycle time, clock frequency? Why is this lower? Right. Associativity is another thing, right? Let's say we just all direct map cache, right? L1, L2, they're both. But also forget about the cache, right? So let's just talk about the smaller SRAM versus the bigger SRAM, kilobyte level SRAM versus a megabyte level SRAM. So what could be more complex, right? That slow down the clock in the SRAM. What's in there? We may have a much larger, much more complex decoder, right? Just to do the addressing. Make sense? Right? That decoder itself might be already much slower, right? It's a much bigger decoder. And of course, right, with the associativity, right, there's another question. If you have a larger cache, right, if you have a lot more blocks, if you have to do the fully associated search, that means we have to search all of them in parallel, right? When we search them in parallel, we also need to make the comparison, right? Eventually, we will only find the corresponding match, right, in one of at most, right, one of the cache ways or cache block. But we need to do actually merge, right, the result. We need to build a much complex computational logic, right, in a very wide AND gate or OR gate, right, or OR gate. That will make things much slower and also a lot more expensive, right, in terms of the area. So that's why usually with the L2 cache, right, it's going to be slower and it's going to have higher miss rate. Okay, does it make sense intuitively? Right, this is really a trade-off, right? It's always a trade-off. All right, so let's see how it helps. Let's look at this example, right? Assume that we have L1, right? L2. Okay, L1 has this pretty good miss rate, right? 3%. L2 has a higher miss rate, 10%. It's decent, not bad, right? But right, this is higher than L1. It takes 1 cycle to access L1 and 10 cycles to access L2. Okay. So what is the actual penalty that we have to pay in this case? Right? How many additional cycles, right, do we have to? How many more? So first, just look at when we miss, right? 0.03. When we miss this one, when we miss L1, 0.03, what's going to happen? What's going to happen, right? We check L2, right? Very good. Okay, what is the, we check L2. So that's 10 cycles, right? And what if we miss? If we miss, this is 0.1, right? So this is a probability that we miss L2. That's unfortunate, right? And that's where we pay this much of overhead, right? What is this? This is basically 0.03 times 10 plus 10, right? Which is 0.6. So the average, yes, the average is 1 plus, you already know, right? This is 0.6, 1.6. This is way better, right, than the CPI that we saw just a few minutes ago. A few minutes ago, we are getting a CPI of 4, right? This is 1.6. This is way better. Okay, any questions? Right, so really, the way to compute this, to calculate this penalty is not that hard, right? So it's pretty straightforward. We just look at the miss, right, on L1, and we need to check L2 regardless, right? That's where we are paying 10 cycles. If we have to miss again, right, that's where we check the main memory. Okay, so this is how this equation is, right, set up. There's some question. John is asking how much more expensive is adding another level of cache, and Gavin asking the same question, right? Yeah, like I said, in modern processors, in many cases we have 3 levels of cache. In some cases we have even more. Okay, we usually have, especially for multi-core system, we have private cache, L1, L2, and last level cache. Okay, and if you look at the microprocessor, it's actually not just about the pipeline. We actually spend a lot of area on this kind of SRAM. Okay, we spend a lot of area, silicon real estate on the cache, because it's indeed worth it, right? All right. So let's take a closer look at how we actually measure the performance. Right. So far we have already seen how to analyze, right, the cycle time. We talk about CPI, but what about the overall performance? So here's the metric, right? In our class, we ask you guys to measure performance of program. We care about the execution time, basically the start and end of the program. And that's usually measured in seconds, right? That's a unit. In some cases, we also look at the throughput, right? So that's basically the total amount of work done in a given time. It's usually the reciprocal, right? Basically, we will want to improve performance, we want to reduce execution time, or increase throughput, right? But for this specific lecture, let's just focus on the execution time. All right, how do we compute? How do we measure execution time? Yeah, we just, right, how to analyze execution time, right? This sounds trivial, right? Why don't we just measure the wall time, right? But how do you analyze it, right? What kind of a processor architecture should we use? What kind of memory, right, system should we use to reduce this kind of execution time for running a program? So let's try to break it down. And this is how we can break down the execution time and break it down into 3 terms or 3 factors. The first factor is the number of instructions, right? The total number of instructions in the program. Second one, this is something that we already know, CPI. Third one, any guess what the CT mean? Any guess? You know, we are putting the number of instructions. Basically, first, we have total number of instructions times, right? This is basically the cycles, right? Per instruction, but this is not a unit yet, right? So if you look at this first two terms, this one cancels out, right? We get a total number of cycles, but this does not directly translate to the absolute time, right? We need cycle time, very good. CT means cycle time. Cycle time really is really the second per cycle, right? Hopefully this makes sense, right? You know, if you actually look at this breakdown, indeed, right, the unit in the end is second. All right, so once we have these three factors, we can actually try to look at each one of them and then make some educated decisions. All right, first, do we want to first we care for the total number of instructions, right? This depends on a number of things. Okay. First, the number of instruction obviously depends on the instruction set, right? Depends on the ISA. Agree? Right? Can you guys give me an example? Right? Where does ISA matter? In terms of, this seems obvious, right? But can you give me a concrete example? How does it matter? How does it impact the instruction count? Even for a given program, let's say this Zoom program, right? We may have 1 billion instructions, or we may have like 10 billion instructions, right, for the total program. The instruction set obviously makes a huge, right, difference. If you think about the example that we have seen before, in our 2300 microprocessor, do we have a hard multiplier? Yes, very good, Stephen. Right? Do we have a hard multiplier in our processor? No, right? We don't have a dedicated multiplication instruction in our processor. That means, you know, to implement one multiplication, we actually have to do this, right? We have to do this soft multiplication or the iterative multiplication. So each multiply operation translates to more than one instruction, right? Translate to 10-ish instruction, which includes a loop. So this is where instruction set obviously matters, right? This impacts how many instructions that we have. In the modern processor, usually we have a hard multiplier, which just takes a single cycle. And also the compiler makes a huge difference in terms of determining the number of instructions, right? Because the compiler is mapping the high-level program into the low-level instructions. The compiler can actually do a lot of optimizations, right? For example, the compiler can merge. We were talking about, right, multiplications, right? The compiler can be smart enough, right, to merge the things into a time state, which is just a shift, right? This is just a shift by 3 bits, left shift. Okay, so these are the things, the main things that determines the instruction count. Cycle time. Okay, we'll talk about CPI later. Cycle time. What are the factors? Instruction set, again, it matters a lot, right? If you indeed implement the very complex instruction, right, which does multiply, add, division, all in one clock cycle, this will hurt the frequency. And the structure of the processor and memory hierarchy also matters a lot, right, in terms of determining the cycle time. Can you guys give me another example? Where does the structure of processor matter? Think about pipelining. Right, in the pipelining, what kind of optimization do we do, which may influence the cycle time? Forwarding, very good, right? Forwarding may add additional muxes, right? May add additional wires into the processor, which influence the cycle time. And also we need to detect hazards, right? So we may decide whether we want to insert bubbles on the fly or not. The hazard unit may also add to the critical path, right? The longest path, which impacts the cycle time. Memory hierarchy, when we talk about fully associated cache, right? Direct map cache, if we plug in a much more expensive cache, right? This may also hurt the cycle time. All right. And let's look at this one, cycles per instruction. This one is actually the even more interesting factor. So this is where pretty much everything comes into play. The ISA instruction set is very important, right, in terms of determining that CPI. Again, whether you do a single multiply or sequence of right, add and shift, that matters. And also the compiler, right, can impact the CPI. I'll give you guys an example, right? You guys should also think about whether that's the case or not. And even the ordering of the instructions, right? That might matter. Why? Even the ordering is important. Think about the delay stop, right? That's something that we talk about. The compiler may rearrange things in a way that right, we don't have to insert bubbles, right? The no in the delay stop. That's just one example. And the structural processor and memory hierarchy matter a lot. Since we have been talking about cache, let's look at cache. Okay, the memory hierarchy. So going forward, when I ask you guys to analyze CPI, so I ask you guys to break it down into two parts. So one is CPI base. The other one is CPI memory hierarchy or mem higher. For the CPI base, so this is the CPI when we have an ideal pipeline, which does not miss in the cache. Okay. It may not be perfect one, right? Because we may still have right? We may still need to deal with data hazard, right? Or control hazard and such. So the ideal CPI may not be one, but this usually is something that I'll give you in the problem set or in the exam. I'll give you the CPI base. So this is where we assume ideal cache, right? So no extra delay when we access the instruction or data. So really the interesting part that I want you guys to analyze is the CPI contributed by the access to the memory hierarchy, which is called CPI mem higher. And these two combined form the overall CPI, which we'll just call it CPI total. Okay. Right? So usually this is a given, right? This one's a given, and we usually want to figure out this one in the problem set that you'll see very soon. Okay, so this is where CPI mem higher is really the penalty, right, that we have to pay when we access the second level cache or main memory. All right, so let's look at a more complicated example. So let's see what exactly is the CPI mem higher in this case. L1 cache, instruction cache. So now we distinguish the miss rate, okay, for instruction cache and data cache. Instruction cache is 2%, right? That's a miss. Data cache miss rate is 5%, yeah, hypothetically, right? So these are the miss rate. No L2 right now. The miss panel is 100 cycles. Okay, and this is the mix of the instructions, right? So over here, the ISA matters, right? The compiler matters, right? It determines the mix of the instruction for the program. So I'm assuming that 20% of instructions are loads and 10% of them are stores. Okay, so how do we analyze this? First, we want to look at the instruction access, right? Because we always need to access instruction. In case there's a miss in the instruction set, we have to stall the pipeline, right? So that's our assumption, because we are waiting for the instruction to be fetched. Okay. So what's the penalty here? First, the miss rate is 0.02, right? Times 100 cycles, right? So this is basically instruction. This is the instruction access. What about data? How do you analyze this? We have miss rate here, right? And we have the miss penalty is 100 cycles. What's missing? Do we have a data access? Do we need to access the main memory for every instruction? It's also related to one of the other questions. Right? No, we do have the memory stage, but it's not like this memory stage will be used, right, all the time. We only access the memory or cache, the data cache, when we have a store or load. What is that percentage in this case, guys? 30%, right, which is 0.3. Okay, this is the data access. So can you tell me the number in this case? The final number? This is a 2, right, plus 0.3 times 5, right, which is 1.5. This is 3.5. Okay, any questions? L1, right? No L2 yet. All right, so this is what we just saw, right? Instruction access, data access. This 0.3 in case you miss, right? So this is basically 20% plus 10%, right? That's how we get 0.3 and 3.5. All right, so if this is fine, let's look at a more complicated case. This is where we have both L1 and L2. Okay, L2 access time is 15 cycles, and the L2 miss rate is much higher at 25%. Okay, and same instruction mix, 30% of them are load and store. Okay, so first the instruction part, right? Instruction access. We have 0.02, right? Times, now that we have L2, right? What should be in the parentheses, guys? What is the miss penalty when we miss L1? We first need to access L2, right? To see whether we have a hit or miss in L2. Then there's a 25% of chance that we have to access the main memory. Right, this is the instruction part. What is this? What is this? This is about 40, right? So if you look at this whole term in the parentheses, basically we have, right, this instruction part, right? This instruction part, this is basically 0.02 times 40, right? Which is what? 0.8. All right. Okay, instruction. We also need to access data, right? In case we have load and store. So what is this? 0.3 again, right? We have 20% load, 10% store. Times what? Times 5%, right? If you have the miss L1, data L1. And same penalty, right? When we access L2 and the main memory. So what is this part? This is basically 0.3 times 0.5 times 40. And what's this? Anyone? 0.6. Thanks. So 0.8 times 0.6, which is 1.4. Okay. Any questions? And this is the instruction access, right? And this is data access. This is the penalty. Right? Compared to the previous one 3.5, very bad, right? Okay. And this one 1.4, way better. Okay. All right. In case this is not clear, I have already included the answer here, the solution here, right? So really convince yourself that, right? So this is the penalty to access the main memory. All right. So this is the memory organization, right? Basically, having L1, L2 indeed impact the CPI a lot, right? So let's come back to the processor organization. Just a few more slides. Let's talk about this. We talk about forwarding, right? This data forwarding. So this one, increase or decrease the CPI? Forwarding, increase or decrease? Decrease, very good. Does it increase or decrease the cycle time? Potentially. Right, possibly, very good, Emily, right? So possibly increase the cycle time, right? Does it, this is data forwarding, right? We are looking at this forwarding, right? Connections. Does it impact the instruction count? Yes or no? No, right? Okay. Right, process organization. This reduces the solve cycles, right? Which lowers the CPI, which potentially reduce the execution time forwarding. Next one. This is where we have, right, remember that we actually change the processor structure, right, the microarchitecture of the processor in a way that we can resolve the branch condition in the ID stage, right? That's a big help, right? So in the end, we only need one delay slot. So which help us in terms of the control hazard. This one lowers the CPI, right? How about the impact on the cycle time? Is it potentially positive or negative impact? Right, everything's a trade-off, right? Everything trade-off. Positive or negative? Potentially increase the cycle time, right? Not instruction time. Ambrose, I guess you meant cycle time. Okay, right, the CPI. Process organization, right? So this influence CPI. Just want to show you one more example. Right? So this is where we look at the compiler's impact, where the compiler moves the thing, right? Moves this independent instruction at I over here to this delay slot, right? This is a delay slot. This helps or this lowers or increase the CPI. Does this help? Or right, this is supposed to help, right? This is supposed to help the CPI. Does this change the instruction count, guys? This is a more subtle question. Does it change instruction count? No. If we don't do the move, right? So we still need to do the add I, right? But what do we need to add here? We need to add a no op, right? So basically, it slightly changes the instruction count, right? Although this is actually not a huge influence, okay? But it does, right? Slightly change the instruction count, because otherwise the processor needs to execute this no op instruction. Right? Okay, does that impact the cycle time? The compiler transformation. This is purely software. Right? Not really, right? No. Okay. So since we have a few more minutes, let me ask you guys one more question, right? Which is a pretty interesting question. You should find it very interesting discussion. Next time we're going to be talking about virtual memory, but since we have, go back to this one. Okay, so since we have a few more minutes, we have been talking about, I think this is an important question to us anyway. We've been talking about this sort of 5-stage pipeline, right? We've been dividing this into 5 stages. This one can increase the throughput, right? The ideal throughput by a factor of 5. But why don't we use a 100-stage pipeline? Why don't we further divide it into 10 stages, 20 stages? Why don't we keep going? Why can't we just go all the way to a very deep pipeline? So where we'll get much higher clock frequency, right? Supposedly, we can further decompose the ALUs, right, into gate level pipeline. We can decompose the RF, right? So we can even pipeline the decoder of the data RAM, or the SRAM, the cache, and everything. So why do we usually, but actually in the modern processor, usually we don't have a very deep pipeline, although it's not 5, right? It may not be 5, it could be 7, 10, 20. But why are we not using a 100-stage or 200-stage pipeline? This is very much related to CPI. What's the issue there? What's the potential showstopper? Of course, again, this may not be feasible, right? We may not be able to pipeline everything into 100 stage and still get the frequency improvement. But hypothetically, let's say we can do that. Right, more registers, right. Yeah, so Steven, good point, right? You're worried about the cost, right? Indeed, cost is a factor, right? But let's say I'm super rich, okay? I don't worry about the cost. I only worry about performance. But can I get good performance, much higher performance, by doing a very deep pipeline? Okay, you're saying increase this CPI. How does this increase the CPI? Errors. Pietro is asking, errors would result in massive delays. Again, let's say I'm super rich, right? I can afford to build a very high-speed pipeline, can divide it into gate level and pipeline it without causing any errors, right? Setup time. I guess Pietro, you are worried about the setup time, hold time violation, maybe, right? Those are not issues. Okay. Same answer to you, Ambrose, and not worry about the pipelining. I can actually, again, this is a hypothetical question, right? I can afford to pipeline at the gate level and still get a high frequency. Okay, this is my question for the class, right? Maybe we can briefly discuss that. I'll give you the answer in a later lecture. Food for thoughts, right? Think about what's the potential showstopper. If you understand, you can figure out why this may not